Okay, so we're going to talk about arithmetic with complex numbers. Now, we've done arithmetic, of course, with real numbers and integers and rational numbers. We want to do arithmetic with complex numbers. Now, the difficulty I find many students have with this is they take things for granted. You need to take the attitude that complex numbers are a new type of object that we haven't worked with before. Of course, you may have in the past, but we have to treat this as a new object. And the operations that you do with complex numbers are new operations, and you need to define them, and in some cases prove them, and don't simply assume that complex numbers behave the same way as real numbers. Okay, so let's go through this and see what we mean. So we know already that complex numbers are represented as a real part plus an imaginary part, that is a real number a plus another real number b times an imaginary number times the I, which we've defined as square root of minus 1. So let's define the addition of two complex numbers. Okay, so we're going to draw on what we know about real numbers. Now, when we add real numbers, we already know how to add real numbers. So, for instance, we know how to add this a and this c. We also know how to add this b and this d because these are real numbers. So I'm going to define, this is a definition, I'm going to define the sum of these two complex numbers as the sum of the two real parts, and that's right here, plus the sum of the two imaginary parts. And the sum of the two imaginary parts is done by taking the real coefficient, the two real coefficients rather, adding them together and multiplying by I. Okay, so again, this is a definition of how to add together complex numbers. Okay, let's go on similarly to a definition of multiplication of complex numbers. Hopefully you can see this on the screen. There, I adjusted a little bit. So here's a definition of the product of two complex numbers. Here is one way of representing a general complex number. Here's another way. And if we did multiply these out using the ordinary distributive law, we would get something like this. Notice here that I'm saying I use Floy instead of foil. You take the first and then the last and then the outer and then the inner. So this term by term expansion of this expression motivates the definition of the product of two complex numbers in this fashion. If you do collect these terms and collect the term and use I squared is equal to minus 1 and collect these two terms together, you would get this expression. This is how we are defining the product of two complex numbers. Okay, so we have addition, we have multiplication. Let's go on to division. All right. Now let's do a special case first. If we divide a complex number by a real number, then we, again, this is a definition. If we divide this complex number by this real number, it's natural to simply divide the real part by the real number and the imaginary part by the real number. Okay, so that motivates, that idea motivates this definition of the division of a complex number a plus bi divided by a real number c. But suppose we want to find the quotient of two complex numbers. You know, we have this suggestive notation when we write a quotient as c plus di over a plus bi, which we could also write as c plus di times 1 over a plus bi. Sorry about the parenthesis here, that's an extra. So what is 1 over a plus bi? Right? So we're going to draw an analogy here with real numbers. When you have real numbers, then 1 over r is called the multiplicative inverse. It's a number that when multiplied by r gives you 1. Actually, you can multiply 1 over r by r on either side and you still get 1. Okay, r times 1 over r equals 1 over r times r equals 1. Okay, another way to write 1 over r is r inverse. Okay. Let's see if we can, by analogy, do something similar with 1 over a plus bi. That means we want to find a number that when multiplied by a plus bi gives us 1. Okay? Then that would give us a good definition for the multiplicative inverse of a complex number a plus bi. Okay, so that's what we're going to look for. We're going to look for a multiplicative inverse of a general complex number a plus bi. Again, we're using a plus bi to denote a general complex number because all complex numbers have this form. Now in this exercise, you're going to show that in fact this complex number satisfies those conditions. If you multiply this complex number times this complex number, you'll get 1. Now be careful about the discussion here. Some people would be tempted to multiply this times the numerator and then divide. But that's not how we've defined things. We have to go step by step. First of all, we have to understand what this means. This is a complex number divided by a real number. And we've shown already how to divide complex numbers by real numbers. That's what was up here. So you have to use 3.2 to explain what this division means. Okay? Then once you've done that, you have another complex number, and you multiply that complex number times the complex number here. Then you have to go back to the definition of multiplication of complex numbers, which is up here. So you have to use 3.2 and the definition of the multiplication of complex numbers. Okay? So be careful. Don't just take this and multiply numerators together and then divide. That's not a legal operation because we're defining anew what these operations mean. Okay, so again, be careful about this. Make sure you understand this discussion. Now in exercise 17, we show that 1 over a plus bi can be identified with this quotient here. And we also said up here that c plus di over a plus bi can be considered as c plus di times 1 over a plus bi. So in order to get c plus di over a plus bi, we simply replace 1 over a plus bi by this expression, and that's where this expression comes from for the definition of the ratio of two complex numbers. Okay, so you'll be using these definitions in your proofs and exercises. Okay, now of course if there's a 0 in the denominator, there's a problem. But that's true with real numbers as well. Right, now this part of the exercise talks about making these expressions a little more familiar and workable. We would like to, instead of writing c plus di times a minus ba over a squared plus b squared, we'd like to write it as a single fraction like this. So we want to show that our previous expression, which was here, is in fact equivalent to this single fraction here. And that's the exercise here. Now it says use equation 3.2 in Floyd. Actually, think about expanding out both sides. Okay? Use definitions and expand out both sides. Okay? All right. So here are definitions of addition, multiplication, division. And we can use these definitions to evaluate these expressions. Some of these may be a little bit challenging. And some of these look difficult, and you'll see later that they're why they work out to be somewhat simpler than they seem to be. So all of these exercises involve playing or implementing these operations, and they should have kind of a familiar algebra flavor. We're going to do more proofs involving propositions of complex numbers. This is actually a version of a familiar theorem from real numbers. What this says is that if you have the product of two complex numbers and that product is 0, then one or the other of the two complex numbers must also be 0. They don't necessarily both have to be 0, but at least one of them has to be 0. And if you think about it, this is also true in real numbers. So here we have an exercise technique that we use often in this class, is to have you fill in the blanks. Now, the key is that this proof is by contradiction that you're familiar with. So when you prove by contradiction, you begin by supposing that what you're trying to prove is not true. Okay, so that gives you a hint on how to start with this. And just see if you can follow through and fill in the blanks. Okay. All right, so now we're going back, and we've talked about operations of complex numbers, and there are certain common features of complex numbers that are common with rationals and integers and reals. They all have an additive identity. This is a number which, when added to any other number, gives that other number. And you can see from this paragraph what the additive identity is. In fact, integers, rationals, reals, and complex all have this, in some sense, all have the same additive identity. There's the notion of additive inverse, which is for any number, there is another number which, when added to it, gives the additive identity. Now notice this important difference, that every number has a different additive inverse, but there's only one additive identity for the entire number system. Okay. So here, if we, in exercise 24, there's some tables to fill in. And you have this associative law, commutative law. So these are the properties of addition for these different number systems. So in this exercise, you'll see the similarities between these 4 number systems. And with multiplication, we can do something similar. So I'm going to skip over that because it's really strongly a parallel discussion. And here's a proof we ask you to do for complex numbers. And we do give you an example 27. Now notice in example 27, for every step we have a justification. And sometimes we're using properties of real multiplication. Here, when we have Floyd, we could also call this is actually the definition of multiplication of complex numbers. So alternatively, I could say or def mult complex numbers. Okay, so that we want you to get in the habit of giving a justification for each step that you use. Okay. All right, so you can do something similar for the associative law. Okay, notice that the last step of this proof here is down here. This is the last step of the proof. These solid diamonds indicate the end of the proofs. Okay. Now you should be able to do something similar for the distributive law. Notice that these are complex numbers, so you should express u, w, and z as a plus bi, c plus di, e plus fi, something like that, and show that this equation always holds for any 3 complex numbers. All right, now this is different from before. Here, when we have we're proving FOIL for complex numbers, each one of these numbers here is a complex number. So you can't just use the old proof that you had before. You have to substitute, you have to express these as complex numbers. So when you write down this proof, you should say, let u equal a plus bi, v equals c plus di, etc., etc., and then show that the two sides are equal using these formats for the complex numbers. You'll have to do some substitution. You have to substitute these expressions in for your complex numbers and then show that both sides are equal. Okay. Now we talk about modulus. Modulus is similar to absolute value. Okay. We know the absolute values in the real numbers, and for a complex number, the definition is a little bit different. You're going to take the square root of the real part squared plus the imaginary part squared. And we'll see why that is a little bit later on. There's an additional operation that complex numbers have that reals don't, the complex conjugate. The complex conjugate of the number a plus bi is the number a minus bi. And there's some examples here. And you're asked to evaluate complex conjugates. So here, all you do is you use all the definitions that you've used before. You have the definition of inverse. You have the definition of complex conjugate. Use those definitions to evaluate these expressions. And I recommend you evaluate them step by step. Okay. Here's a simple proposition involving complex conjugates. In some sense, you could say complex conjugate sort of distributes. The sum of complex conjugates is the complex conjugate of the sum. That's another way you could say this. All right. And notice the style of proof here, because we're proving about things about complex numbers. We write each complex number in the proof in this format, a plus bi, c plus di. We start with the left-hand side, write it out, simplify using some reasons, and end up with the right-hand side. Okay, and you can do these proofs in a similar fashion. Okay, and these are some interesting other properties of complex conjugates. And some more exercises, and some more exercises, and I think don't need to say much about that, and I'm going to stop here.